that. Sorry about that. I didn't know I hit mute. Okay, let's see. What did Antonia miss? Or not much. We just got started. I was saying that this week we're going to talk about, we're going to start talking about modeling nonlinear growth trajectories. And there are a lot of ways to model nonlinear growth trajectories, more ways even than we're going to talk about in this class. But we're going to talk about sort of two different major ways to model nonlinearity. One is to, and I've got sort of two different examples that are highly related. Oh, that reminds me. Pam told me that not everybody knows what orthogonal means. And I'm really sorry about that. And she's like, you know, that's not a word you would use in your everyday life, right? And I was like, yeah, totally. I use it with my kids. I do. Like, my kids know what orthogonal is, but that's just weird, right? No, what? I know. Now that I think about it, I do. I can think of times when I've used it. Yeah, okay. That makes me a total nerd. Anyway, so orthogonal is actually a word that, I mean, it's a stats word, but it especially is used in factor analysis. When you talk about, so orthogonal means that you have, that things are unrelated to each other. They're uncorrelated with each other. So it's basically the opposite of having a correlation. So if you say that two things are orthogonal, it means that they're completely unrelated to each other. And I say that it comes up a lot in factor analysis because if you've ever, who's done factor analysis, exploratory factor analysis? So rotations, remember rotations from exploratory factor analysis? There are two major types of rotations. What are they? Orthogonal, yeah, exactly. Orthogonal and oblique. And the big difference between orthogonal and oblique is that, yeah, the big difference between orthogonal and oblique is that orthogonal forces the factors that you're rotating to be uncorrelated with each other. And when things are uncorrelated with each other, actually, that also means that they're at 90-degree angles, right? And then oblique actually allows those angles to be less. So those are oblique rotations. So anyway, but oblique rotations give you correlated factors, and orthogonal rotations give you. But if I ever use words that you don't know, please do stop me because I don't know. You know, you do this long enough, it creeps into your vocabulary and you forget. It's not a multi-level word, you know, but it's like, yeah, it is. I mean, maybe my kids don't know what it means. Maybe they're just looking at me like I have three heads every time I say it.
I just don't know how. So like unrelated, something you would say orthogonal to the fact that you didn't do your homework.
No. Okay, I can think of an example. I hope it won't be offensive to anybody. Maybe I should like turn off the. But I was saying, so I was having a conversation about like sex and gender, right? And I was like, yeah, sex and gender are not the same thing, but they're not orthogonal either. Which to me is like a totally sensible statement, right? They're related. Yeah. They're not unrelated. They're not completely 100% unrelated. They're also not the same construct, but they're not orthogonal. I think I even might have said that to Jess. I don't know. She was probably just like, I have no idea what you're talking about, Mom. Whatever. I don't know. So I don't know. I do. I use it when I want to say something's not completely unrelated. I'll say it's not orthogonal. I don't know. Maybe that's weird. I never say oblique though. Interestingly, now that this is like a therapy session. I use the word orthogonal all the time, and I say not orthogonal, but I never say they're oblique.
But I think oblique has other meanings for that.
For sure, yes.
So it might be.
Yeah, that's probably why. Okay, back to our regularly scheduled programming. But yeah, I feel like I do. Okay, anyway, back to back to nonlinearity. So we're going to talk about two major ways to fit nonlinear growth models. The first way is to have, basically, we're still going to fit linear models, but we're going to have different, we're going to allow for either discontinuities or different pieces for those growth models. So the first example I'm going to call sort of modeling discontinuity, but I think you'll see it's very similar to the piecewise growth model that we're going to talk about. So we could allow for example, a change in slope or to have two separate slopes. So rather than, so I'm going to draw a picture here. So rather than one linear growth, say there's some growth slope that happens, until, let's say, prior to intervention. But then imagine that something happens here, like event or something, right? And then imagine that after that, I think that whatever this is, this intervention or event of whatever sort, is actually going to change the rate at which people grow. So I'm saying, okay, there's one linear growth slope that happens sort of before that event. And then I'm making this really dramatic, but there's another linear growth slope that, sort of, let's say, starts at this point, and then sort of continues on. And you can see that if you look at that, that is a nonlinear growth slope. But it's a nonlinear growth slope that's actually made up of two pieces that are two linear growth slopes. So the way that we're modeling the linearity is actually, or modeling the nonlinearity using sort of linear pieces, right? So we can model the discontinuity. And in the wages example, we're going to talk about a few different ways to model discontinuity. The second major way, and by the way, you could not just have two pieces. You could actually have, in the example that we do after wages, we actually have a three-piece model. So it looks something like this, where there's like, and again, this is exaggerated compared to what the data actually are, but there's sort of, let's say, low growth, and then there's kind of this spurt period where growth is high, and then the growth becomes lower again. And that would be, you can see there, you could model something like that with three pieces, right? Here's slope 1, slope 2, slope 3. And now the question is, how do you, and by the way, all of the magic of doing these kinds of models isn't in the modeling. So, I mean, there's really not going to be anything very different about the way that you write that one line of code for your multi-level model. All of the magic of this happens actually in the coding that you're doing in your data file, right? Because remember, when we code, what do we do? Let's say let's say we've got 5 waves of data, right? And we want to fit a linear growth model. How do we code? Remember? We recode that. We don't use 1, 2, 3, 4, 5. What do we? Let's say we center, right? We usually center often around initial status. So we go 0, 1, 2, 3, 4, right? So the same thing is going to be true here. When we want to actually code separate time slopes, or we want to code changes in slope or changes in intercept, all of that is actually going to be done before we run the multi-level model. We're going to need to create variables in our data set that basically have the time codes that give us, the system that we want. And so the first thing you do is kind of just like the first thing I do actually is I sit down and I think it out on paper. Like, what do I want these codes to look like? And then once I know what I want them to look like to get the pieces that I want, then I can go ahead and I can put them in my data set. And then the modeling is kind of a breeze. And I'm going to talk a lot more about how we do that in a minute. Okay. So the second, but I do want to sort of just give you the broad overview of what we're doing over the next week or two. So the second type of nonlinear growth model that we're going to talk about is our polynomial growth models. So now this will harken back to your probably high school, maybe, right? Do you remember? I don't know. My kids are doing lots of stuff with polynomial models and like algebra and stuff. So remember polynomial models, right? So we'll talk more about that, but polynomial models will allow us to fit curves. So if I fit like a quadratic model, I actually fit something like that. I could fit a shape that would be like a U shape, right? Or I could fit a shape like this too. We'll get into this when we get into the polynomial models. If I wanted to fit a shape like this, I couldn't actually use a quadratic function because I've got 2 curves. I've got like an S-shaped curve. So I'd have to fit something like a cubic model, something that looks like that. And theoretically, you could go above cubic models you could have quartic models and quintic models. But I mean, generally speaking, I'd say cubic is mostly about as high as people go. Because once you get to a point where you have to use like a quintic model, then you start asking yourself, maybe there's some other thing that I could do to actually model this functional form better than just keep adding these like polynomial terms. Because there are other ways to model nonlinearity. We're just not necessarily going to get to them this semester. But these are probably the two most common ways that people fit nonlinear growth models. Yes.
I think 2 weeks ago we were talking about, and when people got a job, they like jumped down to a parallel slope.
That's an excellent question, and it is different because so there we had an interaction between job and time, right? So the first big conceptual difference that I see there is that you could go back and forth between having a job and not having a job, right? But if you think about what we're sort of talking about here, so that's a time-varying covariate, but here we're really talking about almost like a phase change, right? So like it changes, and once it changes, you can't go back, right? So something like, I mean, and again, that's by the way, that's really tricky too, because if we think about interventions or something, like, are interventions really permanent? I mean, that we could get into a whole conversation about like, when this event happens, does it really cause a permanent change in your slope, or does it actually cause a change in your slope that decays across time? Which again, you could model, but for now, let's not go all the way down there. So I'd say the first big change is that job was a time-varying covariate in the sense that it really could vacillate back and forth. And in this case, we're sort of assuming that this continuity is much more sort of, probably none of you have probably ever done survival analysis, but in survival analysis, there like it comes from the medical literature, right? And death is like usually they call it survival analysis to be more positive, but it's really about modeling who lives and dies, right? But you can imagine if you die, that's it, right? You're not coming back to life. So in survival analysis, once somebody crosses whatever model it is, because you can use survival analysis for other models, but like once you sort of cross the Rubicon, it's something where you can't go back. So the example that we're going to talk about with wages is getting a degree, right? So like once you get a degree, maybe it changes your wage earning, maybe it doesn't, but like that has happened. And so rather than, remember with job, it could have been something like 0101, right? I'm getting a job, not getting a job. But like with wages, it's actually getting a GED. Particular example. And if you get the GED, right, then you have the GED from then on. So that, if you sort of think about that then sort of changes the way that this is going to work. You might be thinking, what the second thing, so that's sort of conceptual. The second thing is more statistical, actually, or so in the jobs one, let's see if we can sort of remember what that looked like, right? We sort of had something that, this is again over dramatized, but this is, let's say, these were the people who were unemployed, and these were the people who were reemployed, right? And we said like, okay, you're unemployed, you're unemployed, here you are, right? And then you get a job and jump down here, right? And so this gap depends on when you become reemployed. But if you think about that interaction, I mean, that's a cool model and it kind of makes sense there, but it doesn't give us, we're not modeling like there's no way to really model in the same sense like a discontinuity that like this event happens and now your slope changes, right? It's more like there are these, again, there are these two hypothetical slopes with a gap and the size of the gap is changing depending on where you are, but that doesn't give you the same kind of idea as like, I'm saying that like, let's say something's happening and then at the, whatever, this I'm going down, 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 and now this thing changes. There is this event, this momentous event, and it really changes my trajectory. And I want to, like here, I can get some interesting predicted values, but I'm not going to get like, what's the change in slope at the moment that this event, right? Or, after this event happens, right? So, it's a good model, makes sense for certain things, but like modeling that interaction between time and the time varying covariate really isn't the same thing as saying, like in this sense, we're really saying there are two periods of time. There are sort of like, there's the period of time prior to whatever, and that there's a period of time post whatever. And they're literally, you're on, like, you have and again, each person can have their own individual trajectories, right? But like you're on one trajectory before this thing happens. Then this event happens, and that deflects you. It changes. Like now you're on a different trajectory after it happens. So that's really sort of conceptually the way we're thinking of this. Yeah. Mm-hmm. Well, so if the event is a treatment, then you got to think about how do you expect the treatment effect to endure across time? So for example, in, like in special education, there are behavioral treatment, like if you work with students who, have special needs, and there might be behavioral treatments that you really believe that like, while the intervention is there, right, and the positive reinforcement is occurring, you expect to either increase or decrease the behavior. But as soon as, shortly after extinguishing the reinforcement, you would expect the behavior to go back to baseline. Mm-hmm. Okay, then that, you can model that discontinuity, right? But that would be different. Just think about it from like this. Yeah, in single subject, you don't really have a model, but you've got baseline, right? And then my phase change line. And now, I don't know, do I want the behavior to go up or down? Okay. Behavior went up, right? There's probably more variability than that, but the behavior went up, yeah. And then let's say I stop giving the reinforcement and the behavior goes down again, right? So in this case, then what you'd be saying is like, okay, there's some slope right here, right? And maybe there isn't. The way it's drawn, it doesn't look like much of a slope, but there's some level, and maybe there's some slope prior to the treatment. And now, like what's really happening, what's most salient in the way that I've drawn this actually isn't a change in slope, it's a change in what? Change in intercept. It's a change in level, right? So that's actually what's really going on here. It's like a change in level. We're going to talk about that too. So we got like a change in level, and maybe there's also a change in slope, but again, maybe there's not. And that's happening here, right? And now I've got another phase change and come down here, right? And so I've got another change in level. And and then maybe a change in slope as well, or maybe not. And again, the way I've drawn it, to me, it really looks like there's a change in level, there's a change in level. It's not really the growth slope that's changing, it's the level that's changing. But no, you could. Well, you wouldn't because you only have 3 people. But if you had like a bunch of people, if you have a bunch of people like that. But anyway, if you have, but you could. But see, what you'd be doing is now this is a 3-piece model instead of a 2-piece model, right? So you're saying there's like a pre-intervention piece, there's a during intervention piece, and there's a post-intervention piece. So absolutely, you could use growth modeling for something. And you could model that. And again, like what looks most salient here is more change in level than change in slope. And in the example that I'm going to give you, we're going to talk about both change in level and change in slope. So that's one example of an intervention. There could be other interventions where you think that, like, let's take reading interventions as an example. Like once you learn to read, you never really learn to unread, right? That's why reading interventions aren't as easy as single subject studies. You can't like withdraw the reading intervention and people won't suddenly like, which is lucky, by the way. This is a good thing. I mean, it's not a bad thing. It's a good thing that people don't unlearn to read when you sort of withdraw the intervention, right? But you can see that that's a very different kind of study that you'd be designing. And with a reading intervention, also, you probably wouldn't expect to see this immediate change in level. With a reading intervention, you might expect to see something like, right? Here I am in the baseline. The kids are not growing that fast in reading. And now, right, I'm gonna implement the intervention, and the intervention is designed to make them learn to read better. But it's not like day one of the intervention, ta-da, you're in the treatment group. Jump up here. No, that doesn't happen, right? Day one of the treatment, you're still like here. But if the treatment is effective, with any luck, then it actually changes your growth slope, right? Your growth slope gets more positive, we would hope, right? And so if that's the case, maybe we see something like this. And so, this is reading growth pre-intervention, and this is reading, during the intervention period. And then again, the question is, if you went out long enough, it definitely would not continue at this level, because again, reading is something that once you get to a certain level, you kind of level off, right? Like, it's not like your reading growth continues to grow until you're, 100 years old or whatever, right? There's a certain level of reading comprehension that's like adult reading comprehension, and after that, so reading in general kind of is more quadratic. So eventually, we probably need some nonlinearity in here, but over the short term, you can see that this would be more the model for something like that. So there's no one right answer to how do you model an intervention effect. Remember when we started talking about growth modeling, I said, it sounds like a trivial, silly question, but it's actually really deep. What is your model for change? Like, your first step when you're doing growth modeling yourself, when you're actually doing longitudinal models, is to say, like, okay, what do I think is going to happen, right? Like, draw it out, like, again, you don't know the intervention is going to work, but like, if the intervention works, what would I expect to happen? And then that helps you to sort of figure out what's the model that you should be fitting, and how are you going to actually model that? And you can think that through before you ever have data, right? So you can think that through, you can pre-register it and all that good stuff. Now, once you have the data, obviously, then you're also going to want to kind of look at your data, right? And make sure that, you're going to look at your data and you're going to model your data to kind of see, like, you may have this expectation, but there may be no discontinuity. You can fit that model and discover that there's nothing, right? But, okay. So questions about any of that? Does that make sense? So our first example, which I think is probably my favorite example here, I really do like it, is this wages example. And we're going to model discontinuity. And I like this example because we're going to learn how to model changes in slope and changes in intercept. And we're going to have this really nice story with some competing hypotheses. So we're literally going to fit 4 models, and we're going to let them battle it out to figure out which model is actually the model that best fits the data that we have. And again, not my data, very old data. Good data, though. It's good. It's a good story. So here's the story. We've got a bunch of people who did not graduate from high school, and they have jobs. Oh, they have jobs. Mostly they have jobs. Anyway, the dependent variable is wages, so we can only actually measure it while they're working. But anyway, so we're looking at their wages across time, and some of the people in the sample are going to get a GED. Some of the people may never get a GED, but lots of the people do get a GED, although it could also occur sort of at any time across the data collection period, this is a long study. I think it's multiple year long study. So this could happen at any time during the whole data collection period. And if you look at the data are actually time unstructured data. So if you look at the time variable, it's actually in years, you'll see decimal places. So it might be like, 0.13, which really means, it's centered actually at the sort of at the start of their work life, or start of the study in their start of the work life in the study. And so, you know, time marches by, right? And they're earning money. And then a bunch of them get GEDs, right? And again, you can't unget a GED. So what, you know, you can sort of imagine this for yourselves. I always say, like, you're doc students, right? What do you think is going to happen to your wage earning potential when you get your PhD? Your hope? What? Did you say down? I hope it's going to be up, right? Now, here's the question. Like, when you get your PhD. Okay, so let's say this is you. Let's say this is you. And so here's your growth slope on the basis. We won't put what the y-axis is. We won't say what exactly that number is, okay? But these are your wages, right? And you do have built in, what is it? What percent raise? 3 or 4%?
Something like that, yeah.
I mean, it's better than it used to be. For union, you know, there's no guarantee.
So there is a raise every year.
There is a raise every year. So it is growing slowly, right? But it's growing. It's not decreasing. That's good.
So if you adjust for inflation.
Whoa. Yeah, it's not, yeah, no. Forget about adjusting for inflation. You know, that's a question nobody would have asked a couple years ago.
Sorry.
All right. So anyway, so we got our wages, and then you get your PhD. How do you think your wages change? Do you think, or your sort of weekly income? Do you think? So I'm going to change the color. So your PhD. Hey. Okay. So now, do you think that they immediately jump up, but then they grow at the same rate? Let's say there's an immediate, I make a big jump. Let's say immediately jump up. Okay, let's say, but like, and pretend, I'm not great at drawing, but let's pretend that these are parallel lines, okay? They're as close to parallel as I'm going to get. So theory 1 would be, okay, we have 4 theories. This is actually going to be our theory 2, but this is model 2, but it's the first one that we kind of talked about here, is immediate change in level, right? So change in level, but no change in slope, right? So I get the PhD, I get my job. By the way, this is probably about what it looks like. Sorry to tell you. Well, maybe the jump, I hope the jump is that big. But like, you get your first job and like suddenly you're making a lot more money, but then from year to year, that faculty or position, you know, also grows at a snail's pace, right? And maybe negative after inflation. All right. So that's option 1. Change in level, no change in slope. You with me? So this is my discontinuity. That means what I really want is like a change in the intercept, change in level. Option 2, well, 2. Let's just get rid of let's just talk about 1 so we can continue on our numbers.
Yeah.
What do you think? 1 is just nothing. Okay. So nothing is like no change in level, no change in slope. That would be bad, right? That's like your worst case scenario. So, okay, here I am. So model 1 would just be, right? I got my PhD and I'm still making the same amount and growing at the same rate. It would be depressing. So so model 1 is really kind of like your worst case scenario. And it's just this is just your simple linear growth model, right? Okay. All right. Now, model 3 is, yeah, right. It goes down. Oh my gosh. Okay. So, wait, hold on. So option 3 is, model 3 is, okay, I get my PhD and there's no immediate change, like in level, but the my growth in salary changes really quickly. So like I get my PhD and I've got this job and I basically start, again, this is not what you're expecting, right? My first job, I make the same amount that I was at the end of my PhD, but But it's still good I got my PhD because even though, well, actually, probably would have been doing that, but put that aside. It's still good I got my PhD because now, even though nothing immediate happens, the growth in my salary is different post PhD or post degree, right? So that is in slope, but no change in level. Right? See? That makes sense. And what do you think number 4 is going to be? Should be able to figure that out by now, right? Oh, yeah, exactly. Both change in slope and a change in level. So let me draw that. Okay, so now we've got, maybe I won't make it quite as severe as last week. Let's say change level. Here we go. Here's my change in level. And I also have a change.
That's what we're all hoping for.
What?
Right? That's
Yeah,
what
that's what we're all hoping for. Big change in level. So big change in level. And a big change in slope. That's nice, right? Okay. Pause here for a second. What if I think the answer is change in slope, but not change in level? And what if that's the only model I fit? Let's say I don't fit these 4 competing models. Let's say I say, no, I think it's going to be for whatever your situation is, which again, maybe is not the post PhD thing because we don't think it's going to be just change in slope. But let's say you say, yeah, I think it's just going to be a change in slope, and I don't think there's going to be a change in level at this discontinuity. And I fit just a change in slope. Imagine this for a second. Let's say this is actually a model 2 where we have a change in level, right? Well, basically, again, have essentially no change in slope. I made them both blue here because I'm going to change the color now. Let's say that's what is really happening. But you think the answer is number 3. There's a change in slope, but no change in level. What's going to happen if you allow the slope to be different? So imagine this is what's really going on, right? But you're going to allow the slope to be different, but you're going to force there to be no change in level. So let's imagine, actually, instead of drawing this as a line, draw it as points. I'm maybe easier to kind of. Let's say we've got boop, boop, boop. So if I fit a model that allows for a change in slope, but no change in level, how am I going to best fit these 4 points if the intercept starting right here? It's going to be a really slow. That's exactly right. Do you see what I'm saying? Because I'm not allowing the intercept to change. And so to fit, even though it's clear when you look at this, that there's no way that that's the right model the way I've drawn it, because I'm not allowing the intercept, like really, if I had the intercept here, which would have a change in level, then this would fit really nicely. But because I'm not allowing for the change in level, what I'm going to get is a big steep change in slope. And that big steep change in slope is likely to be statistically significant. So if your data looked like this, and you ran to this model, odds are good that the slope and the change in slope would be statistically significant. And so you would say to yourself, oh, look, right? My slope is statistically significant. My change in slope is statistically significant. I haven't run any other models. This model must be right, right? Because everything's statistically significant. I'm going to go off and tell this story. But that would be the wrong story. Conversely, imagine this. Imagine you have a situation where there is a change in slope. I'm going to make them dust. There is a change in slope. Okay? And you don't allow for a change in slope. So it's going to have to be that same steepness of slope now, but you do allow for a change in level. What's that going to look like? Oh, it's going to look something like this, right? I can change here, right? But I can't change this steepness. So it's probably going to look something like, right? So again, if you zoomed in on model 2 and you didn't consider what was going on, then you would be like, yeah, change in level, no change in slope. I was right. They're both statistically significant. Woohoo, let's go home. Right? And they would both fit in this scenario better than our sad little model number 1, which is our nothing happened model, right? So model 4 is super important. We've been talking about, partial regression coefficients and controlling for things, right? And you can think about this from that scenario. You can also think about it from the scenario of like, if I don't allow for a change in level, right? What I get is a change in slope parameter is not necessarily going to be accurate because it's just going to be trying to fit what's there. If I allow for a change in slope, but I don't allow for a change in level, right? Again, I'm not necessarily going to get something that's totally accurate. But model 4 is super important because I'm allowing for both, right? So now, when I allow for both, what my change in slope parameter is really going to be the change in slope after allowing for or accounting for the change in level. And the change in level parameter is going to be the change in level after allowing for or after accounting for the change in slope. And so I like to think of it as like you've got these two things and you're letting them battle it out for precedence or priority, right? And they could both be true, by the way. The answer might be both. You need both. But like, you can't really know if you need a change in slope and not a change in level until you allow both to be in the model simultaneously. And if after allowing for a change in level, you need a change in slope, then you need a change in slope. And if after allowing for a change in slope, you need a change in level, right? Then you probably you need a change in level, right? But if you were to only fit these 2 models or these 3 models, you could find yourself in a situation where when you fit model 2, it says, oh yeah, the change in level is statistically significant. And when you fit model 3, it could say, oh yeah, the change in slope is statistically significant, right? And you'd be like, wait a minute, what's going on? And the only way to really get to some sort of resolution is say, okay, I'm going to allow for change in level and allow for change in slope. And once I allow for both, maybe I do need both. Or maybe I really only need one. And after I allow for the change in level, I no longer need the change in slope. Or after I allow for the change in slope, I no longer need the change in level. Follow the logic? Yeah. And of course, I can compare the fit of these models. So I can look, I'm going to look at the parameter estimates, but I can also compare the fit of these models. Are they all nested? Some of them nested. Okay, which models are nested? Yeah, okay. 2 and 4. Well, obviously, what about 1? 1 and 2 and 4. 1 and 3 and 4 are nested, right? But 2 and 3 are not nested, right? Because again, when you think about that, I'm taking out the change in level and I'm putting in the change in slope. So those 2 models are not nested. And in fact, if you do the same, let's assume that if you don't mess with the tau matrix, if you use sort of the same structure of the tau matrix, then these 2 models would actually have the same number of parameters, right? Because you're like taking out one fixed effect and putting in another fixed effect. That wouldn't be true if you messed with the tau matrix, obviously. But and anytime though that you find 2 models that have the same number of parameters, that's a surefire sign that they're not nested, right? They can't be. Okay. So anyway, so we can compare all of these models to kind of get a better, to get a sense of what's going on. And this is kind of what I mean by, you can fit multiple competing models and still have it be theory driven. Like if this were your data, you could absolutely write a pre-registration and say, like, I want to know what, right? I want to know what happens post GED. Here's the approach I'm going to take. I'm going to fit 4 competing models. I'm going to fit a model that says nothing happens. I'm going to fit a model that says after, after people get the GED, they get an immediate jump in terms of their income, but their slope stays the same. I'm going to fit a model that allows for a change in slope, but no immediate change in level. And then I'm going to fit, then again, I think in some way, this is like the most important model of all, right? I'm going to fit this model that allows for both a change in slope and a change in level so that I can see after accounting for one, whether I really need the other. And then I'm going to compare these 4 competing models to figure out which of these models best fits my data, right? Does that make sense? Okay. So, ready to do it? Oh, wait, no, we're not totally ready yet. We got to talk about coding, because that, again, but the really sort of like the magic here, as I said, it really occurs outside the multi-level modeling program. And you don't even see the magic equations here. The magic is in the way that we're going to code time. So let's just start with like a simple example. So let's say I've got time is 1, 2, 3, 4, 5, 6. Okay. And so now let's assume that we're always going to start by centering around the first time. So for my linear model, we already talked about this, right? But that would be 0, 1, 2, 3, 4, 5. So that's going to spell that L there. So that's going to give me my 1 linear growth slope, right? So now let's think about how we're going to code this if I want to allow, let's start with slopes. Let's say I want to allow 1 slope for times, up through time 3, and then at time 3, something's happening, and I think there's going to be a second, right? I want either a second, this is another thing. Depending on how I code it, I can either have 2 separate growth slopes, or I can have a growth slope and a change in growth slope. So I don't know, which one do we want to see first?
2 separate. I
Two
think that's easier conceptually.
All right, we'll do 2 separate.
That was for me.
Okay, we'll do 2 separate first. So let's start with 2 separate growth slopes. So again, imagine that this is let's draw a little picture over here so we can remember. We can remember what we're talking about. Right? So we've got 0, 1, 2, 3, 4, 5, right? And so I'm saying, la, 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 things are going along, I'm growing. And now, put in my little phase change line here. And now the slope, right? It's going to be a separate slope from times 3 to 5. Yeah? So again, I can think of this as slope 1, slope 2. So how am I going to model this? Well, I'm going to need basically like 2 pieces. And the way that I like to think of this, I don't know, maybe it works for me. I like to think of this as, so I think of time, these time variables as like clocks. And they're clocks that I'm going to turn on and off, right? So I need sort of 1 time clock, if you think about it, right? I need 1 time clock to clock the passage of time right here, right? So this is going to be like, call it clock 1, or it's also going to be piece 1 when we're done here. And then I need a second clock that's going to clock the passage of time here, right? And if I want to have 2 separate slopes, right, then literally I'm going to, if you think about it, what I'm going to do basically is I'm going to have clock 1, clock this passage of time up through here. And then I need to stop. That's right. I see Luis doing it. I need to stop that clock. So imagine like you've got 2 little stopwatches, one for like pre-intervention and one for post-intervention, right? I turn on this clock and I let it roll to here. And then I stop that clock and I let this clock turn on, and it's going to clock the passage of time from here on out, right? Are you with me? Yes, great. So now all I have to do is figure out, what do those codes look like? So I'm going to call them piece 1 and piece 2 for our 2 clocks, because again, there are 2 pieces, right? And I want them to be 2 separate pieces. So let's start simply up through 3 here. What do you think? Like, what do I want that, or, 0, 1, 2, 5. Okay, so actually this is times 4, which is 3 here. Okay, so what do you think I want that first? How do you think, this is linear, right? Linear growth through here. So how do you think I want to code that? Yeah, so 0, 1, 2, 3, and I heard some people say 3, 3. That's exactly right. 3, 3, right? And why 3, 3? Because I said I want to stop that clock. So piece 1 only goes through time 3, and then we stop that clock at time 3. And this is why I like the clock analogy. Because when I stop the clock at time 3, sometimes people think, oh, I should go back to 0. Right? Like sometimes the first inclination people sometimes say is like 0, 1, 2, 3, 0, 0. But that's not stopping the clock. That's turning back time to the like original place, which is not what we want to do. Because if you think about it, turning back time would be putting you back here, right? That's not what we want to do. We just want to stop. We want to freeze time at 3. So it's just going to be 0, 1, 2, 3, 3, 3. And then how about piece 2? Same logic. I want piece 2 to turn on at time point 3 and start clocking the passage of time. This is not time point 3. It's at 3 here actually, right? It's like it's at 3 on. Don't let this throw you. Okay. All right. So it's 3 on the 0, 1, 2, 3, 4, 5 scale. Okay. So how am I going to code that? 0, 0, 0, right? 0, 1, 2. Now, you might be thinking like, why is it still a 0 right here, right? But think about it. This is where we're starting. We're starting at this point, and we're clocking the passage of time from that point. So just like when we start with our original growth slope, we start at 0 and we clock the passage of time. After that, we're also going to, start at 0 here and clock the passage of time. And if you kind of look at these codes, you'll see that there aren't, right? Like if you look at this, you can see that we've got like, you look in combination, we've got 0, 0, 1, 0, 2, 0, 3, 0, 3, 1, and 3, 2. So we don't actually have any redundancy there in terms of our codes. Like, which again, you would not want. You wouldn't want to see like 3030, right? That would be kind of cool because then that would be like both clocks are stopped. And we don't necessarily, I mean, I guess maybe there's an occasion where you would want to do that, but okay, everybody with me? Yeah, okay. So next, now imagine that instead of, let me change the color. So come back to black. So you could imagine, let's say that's parallel. This is, so imagine this is our baseline slope before intervention, right? And this is now our slope after intervention. But let's say instead of modeling it as slope 1 and slope 2, maybe you want to model it as the baseline slope and the change in slope, right? What would be some advantages of doing it that way, by the way? Why might you like the baseline slope and the change in slope versus just slope 1 and slope 2? Imagine this is an intervention study, for example. Yeah, exactly, because the change in slope is going to give you the intervention effect, right? And that's really nice. So there, again, there's not, I just want to be clear, not like one of these ways to code is right and one of these ways to code is wrong. It's really going to depend on your research questions and what you want to do and what you're trying to get out of things. But like, there definitely are places where the slope change in slope thing makes a lot more sense. And there are other cases where it makes more sense to do separate slopes. But okay, so now let's say I want to do slope and change in slope. I'm still going to need 2 pieces, piece 1 and piece 2. How am I going to code it now? For slope and change in slope. What do you think? What's the real essential difference here between slope and change in slope and 2 separate slopes? Think about my clocks. off, what's my coding going to be for piece 1? It's going to look just like my linear model, right? You see, it's the exact same coding as it was for the linear model. What's my coding going to look like for piece 2? Yeah, same. 0, 0, 0, 0, 1, 2, right? With me? Does that make sense? And so what's really interesting here, if you think about it, don't let this throw you, is that, okay, and again, these models, by the way, I could do the coding both ways, and these models are going to be statistically equivalent, right? And yeah, I'm going to get a different slope for this, for the second piece, because in one case it's going to be the change in slope, and in the other case it's going to be the actual slope. But mathematically, like you could take piece 2 from the model, right, is going to be piece 2 from the original model. I should have made that black. Make it clearer here. It's going to be piece 2 from the original model minus piece 1 from the original model. When I say piece, I really should be clear. Really talk about the betas here, right? So we're gonna get parameter estimates for these models. And so like these models are mathematically equivalent. They're statistically equivalent. Like the fit's gonna be, the number of parameters is the same. The fit's gonna be the same. And if you do a slope and change in slope model, you can figure out what slope 2 is, because it's just gonna be slope 1 plus the change in slope. And if you do slope 1 and slope 2, you can figure out what the change in slope is, because it's just gonna be slope 2 minus slope 1, right? So these models are not different. It's not like one of these models is better than the other. It's really just about like, which way is the way you want to present the data, which way makes sense for the story, like the story you want to tell, what you're doing, right? You want to test the change in slope for statistical significance. That's a huge advantage to this model. But again, there are other times when that's not what you want to do. It's not an intervention study, right? And so that's not you don't want to be thinking about slope and change. Okay. So, we good? We're good. Okay. So now let's think about the change in intercept, right? Now we have, so we've got this, and now we've got this. So 0, 1, 2, 6, still 3, 4, 5. Okay. All right. So now we want this change in level. How are we going to code that? Any thoughts? Zero, zero. Okay. So 0, change in level. 0, 0, 0. Now here's the tricky thing, is like, right? It looks like this jump is actually occurring at 3, right? So it would be 0, 0, 0, 1, 1, 1. And the question really is, like, I mean, again, when this is your own data, you really need to know, when is that discontinuity occurring, right? I mean, if it's, and you'll see, like in this example, you could have things, when we talk about piecewise models, usually they look just like this, like everybody's got the same time coding. So the way I'm talking about it right now is sort of much more like a piecewise model. But something like GED, different people are getting the GED at different times, and we have time unstructured data, right? So really, continuity should occur at the time point, like immediately after, or, so we're at or after the receipt of the GED, right? So, again, when it's your own data, you've got to kind of think that through, because it could be, you might have something like somebody gets their GED, let's say people are getting their GED between times 2 and time 3, then the discontinuity should occur at 3. If somebody gets their GED right after time 3, then the jump should occur between 3 and 4, right? So you kind of like in your own data have to know, like, where is this discontinuity happening? But again, the way we've got it drawn is like this discontinuity is like it's happening at time 3, right? Again, so we're going to have a 0, 0, 0 here, and then we're going to have this jump. Yeah? Does that make sense?
Or it's better.
Oh.
Similar conditions and then the treatment makes.
I feel like you're thinking of it like almost like a regression discontinuity design, right? But that's a little bit different because in that case, X is like the X-axis is your running variable, right? You got different people on either side of the X-axis. Whereas here, we're really talking about one, like every person's going to have their own trajectory. So you're going to gain a lot of information by modeling every person's full trajectory, right? And then we're going to kind of aggregate or pool across people. But yeah, I know exactly where you're coming from. With RD, it would feel like you should just do this, right?
Yeah.
But we're gonna get a lot of information here because it's within subjects kind of thing. Okay, is everybody good? Does this make sense? All right, cool. Is there anything else I want to say? I don't think there's anything else to say about this. So, yep. Oh, change in level and change in slope is going to be this. I'm just going to put them both in together. Yeah, I should have said that. So sorry for not saying that more explicitly, but yeah. So change in slope, change in level, change in slope and level, I put both in, right? I put both sets of codes in and I let them battle it out.
And
Yes.
And you could use either version of the slope coding. She just circled
Yeah,
that one.
yeah, I circled this one, but yeah, you could use either version. You're not going to use both versions of the slope coding though. Yeah. Oh, okay. Yeah, that's a good question. So, you may not remember this, but remember when we talked about the intercept and I said that like technically when you model the intercept, like if you had a design matrix for regression or for multi-level regression, whatever, in the design matrix, you actually have a column of ones for the intercept. And so remember that when we have our combined model, like our of TI is equal to beta naught, right? Plus beta 1. Let's just stop here for since I run out of room. Right? But remember that beta naught doesn't get multiplied by anything in our model. Like the intercept always stands alone. Why does the intercept always stand alone? Well, it is actually implicitly getting multiplied by 1. And I think I'm going to show you when we get into R. I've got the code where we can see the design matrix, which will be helpful for these models to just make sure you kind of set them up the way that you want. So implicitly, our intercept is 1 times that beta naught, right? And then if you think about this change in intercept, right? So what we're doing is we're saying I'm allowing for a second intercept. And that second intercept is going to be 0 before it turns on. And then it's also going to be a set of 1s when that second intercept, when that change in level comes on board. So do you see what I'm saying? So in some sense, we do have, like you could think of this as, this is like intercept 1, right? And then this really is going to be, it is really going to be a change in intercept because the intercept is always coded 1, 1, 1, 1, 1, 1, 1. So there's no way to do this like, oh, is it a new, I mean, I guess you could actually do this. I'm not necessarily recommending it, but there are occasions where it makes sense. If you literally wanted 2 different intercepts, like you wanted to wipe out the first intercept and say there's 1 intercept pre and 1 intercept post, then you could go like, you'd have to create your own design matrix and you'd have to basically say this intercept is only salient until this time point, and then in the design matrix you'd have to have 0s for the first intercept and then 1s for the second intercept, and that would literally give you 2 separate intercepts. But like people don't normally do that. I mean, again, there could be an occasion where that makes sense, but as default, I would not go there. Just think of it as intercept and change it. because normally we always have an intercept in our model, right? Like 99.99999% of the time. And what that would, so anyway, so that's why we only have one coding scheme, because we really are thinking of it as intercept and change in intercept. Whereas with the other one, we can think of it as slope and change in slope, or slope 1 and slope 2. But that was a good question, actually. Maybe you're sad you asked now. Yeah, other questions? Yes, Claudia. Which part about the, that's a big question. Which, can you help me narrow it down? Oh, the red square. So I was saying, oh yeah, so the red square was, I was saying, the question was, well, how would I code the change in slope and change in intercept? Like model 4, what would that look like? And if I'm doing change in slope and change in intercept, model 4 is putting in these 3 codes all together. And then Pam said, remember, if you wanted 2 slopes and a change in intercept, right, then you could put in these 3 codes all together, rather than the change in, like what we're going to do for wages is actually going to be change in slope and change in intercept. And what we're going to do for this model is very much this. The next model that we do is going to be much more like 2 separate. Well, actually, it's going to be 3 separate slopes. So this fits what we're about to do. So we would put in these 3 pieces. So if you think about it, for model, like the 4 models that I talked about, what pieces would go in for which model? Like we could just stay with these 3 pieces here. What piece would go in for the linear model? Just piece 1, right? I mean, I could go back and use my linear time variable, or if I, but that's going to be the same as piece 1 here, right? For model 2, what's going to go in for model 2? Which was the change in level, but not a change in slope. So I would put in this piece, right? And this piece, but not this piece, right? For the change in slope, but no change in level, I would put in these 2 that we talked about, right? And then for model 4, that lets everything battle it out, I'm going to put in all 3 of these at the same time. Yeah? Make sense? All right, cool. And then one other thing we got to kind of think about that we haven't talked about is the tau matrix, right? Because as I add more slopes, they could be randomly varying, or they could be non-randomly varying, right? I mean, or they could be, they could not have random effects. They could have random effects or not have random effects. They could be fixed too. So they could be randomly varying or not. So now I think is a good time for us to talk about how many random effects can you support in a growth model? Because I don't think we've had that conversation yet, have we? Okay. I think I have all of this. I can't remember now if it's in this packet or the next packet. It doesn't really matter. We'll talk about it now. Okay, so you remember way back when I said, if you have a linear model, right, or if you have 3 time points, you can fit a linear model. And you can't fit anything more than a linear model. You remember that? I didn't really explain why that was. I mean, I kind of explained, I sort of did the whole, which is true, that like with 3 points, right, you can fit a straight line and you can have some error, remember? And that if you only had 2 points, there would be no error, which is true. That's all still very true. But there's another way to sort of think about that, and I think it'll be helpful. And the question is like, how many random effects can my model support? And this is going to be more salient when we're talking about longitudinal models, because we often have very few observations per cluster, which is a person, very few observations per person. So imagine that I have 3 time points. And so let's think about what, if I were going to create a covariance matrix for my data across time, not for my taus right now, but like for my data. So I have 3 time points. And so I have right, I've got whatever it is, math at time 1, math at time 2, math at time 3. Variable at 3 time points. What would this variance covariance look like? It would be like the variance of that variable at time 1, the variance of the variable at time 2, the variance of the variable at time 3, right? And then I'd have the covariance between 1 and 2. I have the covariance between 1 and 3, and I have the covariance between 2 and 3, right? So if you're sort of thinking about sort of like how many pieces of information do you have sort of to model, how many do you sort of have to sort of model your variance covariance components? This is kind of putting an upper cap on it for you. And I'll explain more in a second. So now let's think about if I have a linear model and I'm going to fit an unstructured tau matrix. So here's my tau matrix. Okay, and I've got a linear model and I want to allow the slope to randomly vary and I want to allow the intercept to randomly vary across people. Then I'm going to be fitting tau, not, right? Tau 1, 1 and tau not 1. But I'm not like totally done yet because I also have one other variance that I'm fitting in my model, which is sigma squared, right? So, and if you think about this, these are like our residual matrices, or sorry, residual matrix, and we've got sort of sigma squared here. And these two things together actually are used to create the composite residual matrix, which I'm not going to talk about the composite residual matrix in any detail right now. Maybe we'll talk about that in another week or two. I want to. Let's see if we get there. But for now, just trust me that my composite residual matrix, it can't be bigger than this, than the sort of the matrix, the variance covariance matrix of my variables across time, which kind of makes sense, right? Like this is kind of like my upper limit. So if you think about it, here I'm estimating 4 parameters. And here, and again, if you've taken SEM, this is going to, you're like, yeah, totally makes sense. I totally jam on this because it's like back to the old days talking about variance covariance matrices, right? So here, how many pieces of information do we have? 6. So again, to harken back to when I talked about this in SEM, I would say we've got 6 knowns. We've got 4 unknowns, right? And so I actually have, like, you could sort of think of this as, plus 2 degrees of freedom, right? I have 2 more knowns than unknowns. So what we would say is that this is over-identified. It's really what I'm really saying, again, at a very deep level, what I'm really doing with these taus and the sigma squared is I'm taking these taus and the sigma squared to basically, and my fixed effects, to reproduce, right? To sort of reproduce this. Or just think about taking the taus and the sigma squared, actually, forget about fixed effects. Think about the taus and the sigma squareds as reproducing the composite, this sort of composite matrix, this composite covariance matrix. Okay. So that's great. I'm in good shape. No problem. What if I wanted to put in an extra randomly varying slope? Well, I did that. Okay. So now I have 2 randomly varying slopes and a randomly varying intercept. And at first blush, you might think, oh, I'm fine. I have just as many taus as I have elements in my sort of original variance covariance matrix. But I'm not okay. Why? Oh, it's that pesky sigma squared, which I need. It's that pesky within person error. And in fact, again, we won't go down this road, but like, if you're really desperate for an extra random effect, you could theoretically like fit a model where you don't estimate sigma squared. You fix it to a known value, but that's a risk, as you can, like, just even saying it, I see people's eyebrows going up. So that's a really risky proposition. These are not the things you should do lightly, right? I mean, well, actually in my dissertation, I did exactly that. I needed an extra slope that I wanted to randomly vary. And so I ended up sort of precision weighting sigma squared. But again, it's not an everyday occurrence, and not something you should do unless you've got a really, really compelling reason to do it, and unless you really, really know what you're doing, because it is kind of a dangerous thing. So under normal circumstances, 99.99% of the time, because we've got the sigma squared here, you can see that you're never going to be able to fit as many random effects as you have time points. Like, think about this dimension as being basically t by t. It's like the number of times you have, right? And this dimension is sort of like r by r, where r is the number of random effects, right? And because of sigma squared, if the number of random effects equals the number of time points, you're always going to be one short. You're always going to have -1 degree of freedom. You're always going to be under-identified. And that's why the rule of thumb, you'll hear this rule of thumb, that you can only fit one fewer random effect than you have time points. And that's exactly why it is, because if you try to fit as many random effects as you have time points, you're going to be under-identified. Okay, sure. Okay, imagine, right, the number of time points, this t by t matrix is sort of giving us this upper limit, right, of how many variance, covariance components we can estimate. So think of t as a number of time points, right? And then think of r is equal to the number of random effects. Model. And when I say random effects, I'm not just talking about slopes. I'm talking about the intercept too here, right? So just the total number of random effects, randomly varying intercepts and slopes. And you can see that, like, if you have as many random effects, you try to fit as many random effects as you have time points, the tau matrix is going to be the same. It's going to be the same size as the sort of this, this variance covariance matrix that we're talking about. This sort of, just think of it as like the variance covariance matrix of the outcome variable across time. I think that's the easiest way to think of it. So those will be of the same magnitude, but the problem is that you have sigma squared. And so because you need to estimate sigma squared plus the tau matrix, if you try to estimate as many random effects as you have time points in the longitudinal model, you're going to end up being one parameter short. You're going to have like -1 degree of freedom, basically. You're going to be one parameter short. And so that is why you can't actually estimate as many random effects as you have time points. So the general rule of thumb in growth modeling, whether you're doing it in SEM or in multi-level, is you can, well, I guess it's different in SEM because you're doing factors. But anyway, so let's stay with multi-level. You can estimate one fewer random effect than you have time points. So if you have 3 time points, you can estimate 2 random effects, and that's going to be a randomly varying intercept and a randomly varying time slope, and then you're done. You can put in, now remember we said you can put in time varying covariates. You could put in other like time varying covariates at level 1, and when I say time varying covariates, I mean variables that vary across time within person. But if you only have 3 time points, you're not going to be able to estimate a randomly varying slope for those time varying covariates, right? So it doesn't necessarily mean that you can only have time in your level 1 model, but what it means is you can only have one of your level 1 variables, and usually the one you'll choose is time. You can only have one of your level 1 variables randomly vary across time. Yeah, or across people, sorry, I didn't mean across time. Yeah.
I'm still confused about like why they. Are you?
Well, no, I mean, and again, we're not going to get, I mean, I would love to get into this right now. I'm not going to get into it right now, but basically what ends up happening is that you take this sigma squared and these taus to create what is a composite residual matrix. And the composite residual matrix, it can't be bigger than like, sort of like just the regular old variance covariance matrix for the number of time points. Because like, if you sort of stop and think about it, it's like, okay, well, I'm trying to do all this to fit my data, right? But like, if I try to break this into more pieces that actually sort of exist in the data, that's sort of the like high level conceptual way to think about it. Right? There's no way to do that, right? I mean, even thinking about, again, I feel like at this point in the semester, you're all taking for granted that we can have like a bazillion taus, but stop and think about it. Just take a step back and remember that with Eric last semester, you just had little bitty sigma squared, right? This was it. This was all you had. And now it's like, we got all, like, we're taking our residual, right? Breaking it into a bazillion pieces. But there's a limit to how many bazillion pieces we can break our residual into. And it really is that you can't, I mean, a good way to think about it is you can't have more random effects than you have level 1 units. Think about it that way. Like, so if time is, but here, or not level 1 units, observations at level, like within a cluster, within a person, level 1 unit. I don't mean total level 1 units. I mean like within person. So like, I can't, and this would actually be, this is true actually. For organizational models, it just doesn't rear its ugly head as quickly because usually in organizational models, we have like 20 or 30 or 50 people in the cluster, but it's absolutely true that you can't have more randomly varying slopes. You can't have as many randomly varying slopes as you have like level 1 units within each level 2 cluster. Now, it turns out if your question is like, what if like a couple people are missing the third time point? Like, is that yeah, it's fine. Like if you've got a little bit of missing data, that's not going to be a problem. But like, you need to sort of have a design in which you're expecting that, people are going to, you're collecting data across 3 time points for most people or whatever. So it's because we have so few level 1 units per cluster, which is person, that's really what's limiting the number of random effects that we have. And this is really telling us, like, we only have this many. Think about it. We only have, like, you don't want to think about it as this. You don't have to. You can just think about it as, like, how many time points we have. Time points equals 3. Okay. If there are 3 time points, then I can only estimate 1 fewer random effect than I have time points. Because I can only ever have 1 fewer random effect than I have, like, level 1 observations within a level 2 unit. Yeah. Yeah, you would just, I mean, I don't know what the exact error message would be, but yeah, you would get something about, the model can't, it wouldn't converge. It would give you it would kick some sort of an error message, and I don't think you would get any kind of results. Yeah. Yes, Claudia. Yeah, like in this case, I was just saying, like, imagine you had whatever your variable is, time 1, time 2, time 30, right? So you could sort of imagine thinking about, what is that sort of variance covariance matrix look like for your outcome across time? And that really is kind of putting an upper limit on how many taus and how many variance components you can fit. Yeah. Yeah, you could. You could, like, another, that would be a totally, that would be a more common way to do it. So you could totally constrain, I mean, I'm not saying you should, but you could totally constrain one of the, like, and we've talked about that already, right? Like, you could theoretically, the easiest sort of, you could fit a model where you only fit the taus and you don't allow for the covariances. Now, I told you there are some big downsides to that, right? So that is also something you should not enter into lightly. Or you could say, okay, I'm going to fit, these taus and this tau, but I'm going to get rid of these taus, right? You could do that, but there are dangers there too. So I think it's much safer to, as a general rule, unless you're really, 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 you know what you're doing and you feel confident that it makes sense and that you can defend it to the hills, like I would not recommend doing that, but you could. That is another way to buy some space back, right? Another thing you could do, again, I'm not saying you should do this, but you could constrain some of them to be equal to each other, right? That would buy you some degrees of freedom. I mean, there are lots of things you could, in theory, do. But again, as a default general practice, I think it's best for you to say, unless I know what I'm doing and I've got a really compelling reason to do otherwise, I'm only going to fit one fewer random effect than I have time points. If I get tempted to do something else, I will promise to go consult with somebody who knows this stuff. Yeah.
But this is assuming that we.
Which matrix are you talking about? That matrix or this matrix?
Like,
Oh.
we'd be adding to.
No, it doesn't, because, okay, so this is where this matrix isn't identical to the matrices we talked about in SEM. Because in SEM, you remember, we talked about having like this variance covariance matrix that was all the variances and covariances for all the variables. That's not what I'm saying. This variance covariance matrix, think of this as literally just the outcome variable, right? The outcome variable across time. And because, again, if you think about it, it's because these are all residuals, and these residuals are all residuals about the outcome variable. So it doesn't matter how many covariates I have, right? So in some ways it's very similar to SEM, but in some ways this is kind of different the way we're thinking about it. So I could have tons of covariates, but that doesn't buy me anything in terms of sort of how I'm going to model the residuals in the outcome variable, because there's still one outcome there's still the outcome variable measured across this many time points. So the more time points, this is why in longitudinal models, having more time points is so useful, because the more time points you have, the more flexibility you have with how many randomly varying slopes you can have, right? And if you have few time points, you can put in a lot of covariates, but it doesn't actually buy you anything more in terms of like sort of the structure of the residual variance covariance matrix. Yeah? Yes, Marcus.
In terms of community.
From an argumentative point of view?
Yeah.
Okay. Okay. As an argument, not necessarily argumentative. Gotcha. All right. That's what I thought you meant.
He's gonna argue with you, Beth.
All right, go ahead. I'm with you. Oh, totally agree with you. Like, I agree. So like Marcus's point is like, that's a lame argument to just say, I fixed this stuff because I don't have enough time points to do otherwise. Because if I were a reviewer, I might say back, well, then you should have gotten yourself some more time points, right? Like if you think that you really need to be allowing this thing to randomly vary across people, you should have collected more time points. And that's why I know, like, this is a horrible thing to say, because longitudinal research is incredibly expensive and time consuming. Obviously, that kind of goes without saying, but like more time points is better. And, there's also a trade-off. We'll talk about some of this when we talk about power. But if it's true in any multi-level model, but like, are you better off having more people and fewer time points, or are you better off having more time points and fewer people? Now, there is a point below which you dip on people, like let's say the single subject studies where you only have 3 people. That's not enough, but there's a point below which you dip where it's like, well, yeah, I would like more people. But you're generally better off having more time points per person than you are having more people, especially, that's not necessarily true if you just want to fit a linear model, but that's certainly true if you want to fit a more complex model. So your point, though, was, what do you say back? What's the argument you make? Well, I know the first thing is you don't do that, right? Like if you think you need more time points, you should collect more time points. But what if you, I mean, yeah, you're kind of stuck, right? Like, what if you have this model where you really truly believe, for example, I mean, this happens. What if you have only 3 time points, but you really believe the trajectory is not linear, right? And I mean, again, if you really believe the trajectory is not linear, you could put in a nonlinear piece, but you can't allow it to randomly vary across people. So that's not so useful, right? Yeah, I don't know. Like you're stuck. I mean, you're right. That's you find it's not a compelling argument for why you're not. It is true, but it's not satisfying to say I fit this model because I didn't have enough data to fit the model that I really wanted to fit, that I think is actually the right model. You know? Ugh. Okay. Yes. Is it break time? Don't tell me that. Okay. That's all right. So we'll take a break for 10 minutes. And then when we come back, we're going to fit the wages data and we're going to find out which model fits the best. And I was right. We're not going to get to quadratic and cubic models.
Calculate all the tolls.
Well, we're estimating. This is another parameter in our model, right? No, knowing all the talents. So these are all the parameters. Remember, we're all estimating all these parameters. Oh, we can't estimate more parameters here than we have.
That's right. I understand.
Yeah. No, but normally like sigma squared is kind of like in multiple regression, this is the one that's most analogous to our regular old like residual variance in a multiple regression. It is usually the biggest of the error variance. So yeah, we can't just assume that we don't have this. If anything, this is the last one that should go generally.
So the
That's all of this is being estimated by the likely. Yep. All right. Okay, so aren't you all excited to find out what's going to happen with our wages example? Anybody have any hypotheses? Don't cheat and look at the R markdown file. What do you think? Oh, don't cheat. Anybody want to put money down? Change in level, change in slope, both, neither? No? Okay. Both? Oh, okay. All right. At least one person took a stand. All right. What? Yeah, right? Okay. So let's go ahead and go through this example. And so I am not going to go through all of the text that's in the beginning of this document, but I did try to write down most of what I just told you before the break, I hope. I think you'll see that there's a lot of, and again, I'm looking at this, not at what's on the screen. So I think that you'll see that the first, like, I don't know, 5 pages at least, I think is pretty much a repeat of what we talked about. But let's take a look at the bottom of page 4, and let's just quickly look at sort of what our model looks like for the change in level, because we didn't talk about the equations. I mean, there's nothing really new here, and with any luck, I think I checked, and I think I did better on my subscripts today. So, but here, so our outcome here is that it's the natural log of wages. It's pretty common for wages and income and stuff to end up getting transformed. We don't care about that particularly right now, but that's why it's LNW. It's the natural log of wages is equal to, so this is the model for change in level. The model, I don't even think I wrote out what the linear model looks like because it just looks like a linear model, right? But for the model for the change in level, we have the intercept. At level 1, we have the intercept, right? And then we've got experience. So this experience is the time variable in this case. And I think I mentioned that it's time unstructured data. So it's going to look a little different when you look at it than it looked up here in our example where I was writing everything out with like time structured data and everybody had sort of the same, pieces. So what I wrote up there is probably more what I would call like a piecewise model. But so it's going to look a little bit uglier, but that's fine. It doesn't matter. So we've got experience, right, is our time variable. And then GED is our pre-post GED. It's our change in level variable. So GED is coded 0 before you receive the GED and 1 from the time you receive the GED on. So basically, the change in level model has this, just the regular old time variable, which is experience, and then the change in level variable is GED, which is 0 prior to receiving the GED, and 1 once you receive the GED, right? And we're going to allow all of those pieces to randomly vary. So if we're allowing the intercept to randomly vary, we're saying that people are going to differ in terms of what their wages are when they start, like at the beginning of, right, of the study, or at the beginning of when they're earning money or whatever. And if the experience slope randomly varies, then we're saying that different people, like people's wage earning slopes grow at different rates, right? That makes sense. And if we're allowing the GED slope to randomly vary, what are we saying there? There's variability across people in terms of, remember, it's the change in level. So we're saying getting the GED has a different impact in terms of raising your wages for different people, right? So if I didn't allow the GED slope to I could fit a model where GED slope doesn't slope, I'm calling it slope, it's a change in intercept, but it's still a slope, right, at level 1. So if I didn't allow that GED variable to randomly vary across people, then I'd be saying that the jump that you get by getting a GED is equal across people. Like everybody gets basically the same amount of an increase in wages when they get their GED. So that change in level would be the same across people. But it kind of makes sense that you wouldn't think that, right? Because different people are working at different jobs. There might be some jobs where some people don't get any change in level, and other jobs where people get a big, like some people's wages might not change at all. Other people's wages might change a great deal. The fixed effect is really kind of like the average, right? Sort of the expected value across people. But I would kind of expect that there would be variability across people in terms of how much of a difference it makes getting your GED. Does that make sense? Okay. So we're allowing that to randomly vary across people. And then because we're allowing that to randomly vary across people, right, then we've got 3 random effects. And so we actually have, a tau matrix that has 6 unique components in it, right? And so I wrote out how many total parameters we have in the model, which are, we've got 3 fixed effects, right? The intercept, the experience slope, and the change in level, plus our 6 taus, plus our sigma squared. So this model is actually 10 parameters that we're fitting. And so how many time points would we need, by the way, to fit this model? What would be the minimum number of time points we need across? Yeah, 4. We need at least 4 time points, right? Which in this case we have. I think we have like way more than that, actually. It varies by person, but I think most people have like 6 or 7 or so time points. Okay. So then for the change in slope, again, the model, the model is going to look very similar in terms of the number of parameters we're fitting, right? The big difference, if you turn to sort of page 6, is for the change in slope model, we're going to take out the GED variable, that is that 0, 1 variable, and we're going to put in a post-experience variable that is clocking the passage of time after the GED, after receiving the GED. So it starts at 0 with the GED, and then it clocks the passage of time after the GED. So let's take a look, and then let's see. And then finally, we're gonna fit a model 4, where we have both. If you look at page 9, we're gonna put in GED, experience, and post-experience, right? And we can sort of fit that model. Now, if we allow all GED experience, post-experience, right? There's a lot of stuff going on there, right? We've got a lot of things that could potentially randomly vary. I think you're going to see as we go through this, we're going to have to think a little, I mean, just for our own sanity, we're going to have to think a little bit about which random effects we need. But okay, so let's start by getting, scroll down. So, oh wait, I just need to make sure. Data here. Scrolling down through. So the whole first thing is really just like sort of setting all the stage. So I'm line 372. That is where we're going to read in the data. And it's probably helpful to kind of just look at our data for a second so you can see what this looks like. So again, so ID is the person ID, so you can see like person 31, we have 2, 4, 6, like that. I don't know. Natural log of wages is our outcome variable, and you can see like it looks funky, but that's because it's on a natural log scale. Experience is like the number, as I said, it's in years, and it's the number of years of work experience. So if you look at person 31, like at their first time point, they have very little work experience, right? And then now, in this particular situation, remember, time varying covariate doesn't have to necessarily vary across all people, right? So this is a person, if you look at 31, this is a person who actually had their GED, weird. But anyway, this is a person who had their GED from the get-go of the study. And there are, and I think I've actually got in the handout, I think I break out for you how many people always had their GED, how many people never get their GED, and how many people change from not having a GED to having a GED. Because again, that's kind of an important thing to know, because if it turned out that everybody either always had it or never had it, it would not actually be a good variable to try to use in this way, right? But so anyway, this person always has it, but for other people, you'll see it'll be like GED is like 0, 0, 0, and then 1, 1. Right? And then look at the post experience for this person. Because they always had the GED, their post experience variable looks just like their experience variable, which makes sense, because remember, the post experience variable is going to turn on at the point at which somebody gets their GED, and then it's going to clock the number of years of experience after receiving the GED. So in this particular scenario, this person, like their post experience and their experience, again, we're not really going to be able to get it like a change in slope for this person. They're not really going to give us anything, but we are going to be able to get that overall because we've got plenty of people who change. So, but let's look at somebody, let's scroll down maybe and look at somebody who does change across time, just so you can kind of see the coding in action. Yeah, here we go.
134.
I was going to say 134. This person, okay. Person 134, sure. Oops, wait, let me go back up to get to the top of 134. Okay, person 134. Yes, this is a better example of somebody, right? So person 134, you can see again, here's their natural log wages, right? Here's their experience variable. And so they're coming into the study about 0.192 right, years after they started working. So that's why it's coded that way. GED at this point is a 0 because they haven't received their GED yet. And so their post-experience variable is 0, right? And you can see that it continues that way until we get to, when they have 3.915 years of experience there, right? They now receive their GED. So at this point, they're getting their GED, and their post-experience clock is now turning on at 0. They've received the GED, the post-experience clock is turning on, and now if you look at this, right, you can see that like from 3.915 to 4.635, what's the difference between those two? It's 0.72, right? So now this is clocking the passage of time from the receipt of the GED on. So like they're starting at 0, and now it's been 4.6 years since they've been working in general, but 0.72 years since they got their GED. Right? Do you see what I'm saying? And now here, on this next one from 4.635 to 5.635, right? They've been working for 5.635 years. They've had their GED for 1.72 of those 5.635 years. Does that data make sense to people? And again, this is what's so important when you're doing this kind of work, is because like it's really important that all of this be coded correctly. Doesn't, if your data don't make sense and you don't have them coded correctly, then then the modeling part is not going to give you the right answer. So you want to be really fastidious about this. Okay. Questions about that? Does that make sense? All right, cool. So, all right, so going back to so everybody should have oh yeah. So I did actually, if we run this, here we go. This is just for your own edification, like how many people actually got their GED at some point during the study. And so, again, like in some sense, it would be nice if there were more people, but a little less than half of the people actually got their GED during the study. So there are a fair number of people who actually are not changing, which is, again, not ideal, but we're gonna ignore that because it makes such a nice example. Okay, and there are a whole bunch of plots in here. We're gonna skip through the plots. You can see the plots. Okay. So here here I set up the code for that post-experience, here I'm talking about the code for the post-experience clock. Actually, set up the code here, but I'm just talking about the code. There's really not anything too interesting there. We already just talked about this idea that you can, if you look at experience minus post-experience, that you're really gonna kind of see what's going on. Okay, so now let's run our models. You ready to run models? Okay, so the first model is going to be really basic model. It's our linear growth model. So this should be like old hat here. So there's nothing different here at all. But I think, and I am going to make you write some stuff up on the board, Pam and Jen, so we can keep track of our like model fit. So, but this is a good model because it's our baseline model. And this should be, I would expect this to be our worst fitting model, right? This should be the model that has the highest deviance. Okay, so let's go ahead and run our model. And here we go. So, where'd my deviance go? Okay, so the deviance for this model is 4921.4. And that's probably enough. Yeah, write that down.
And this is model one.
This is model one. The deviance is 4921.4. We'll just keep track of the deviances. And right now, let's just also quickly look at our fixed effects and just make sense of them. Because I think, again, just get our heads in the game. So we've got intercept is 1.7, let's call it 1.72. So again, that seems weird because it's in a natural log, but okay, so we just start at like 1.72 and they grow at a rate of about 0.046 points per year. They grow at a rate of about 0.046 points per year. And again, we're not allowing for change in intercept or a change in slope here, right? And I don't know, there's not too much else we want to say about the linear model. Just kind of getting our head in the game, getting our basic. Oh, but I do want to show you this. Okay, I did not include this in your R markdown file for obvious reasons. But this is just, if you ever want to see what the design matrix is for your study, remember I was talking about the design matrix, which I think can be really helpful when we're talking about these models. Oh, there it is. And actually, it stops at like 1,000, but that's fine. We got the idea with the 1,000. The model matrix shows you the model's design matrix, which is actually where we will see the way that we've coded. Like we'll see all of our, the first column will be ones because that's the intercept, right? And then after that, we'll actually see all of our covariates, all of our level 1 variables. So it's really, it will show you what the coding is for like the change in slope and the change in intercept models. Now, right now, I did the model matrix for our first model, which was our linear growth model. So if you look, kind of hard to see because it just got stuck down there on the bottom, but I did not want to put it in the R Markdown file because it would have been such a waste of space, right? But here, if you take a look at this, here's the matrix. Okay, and you can see, like, remember the first person that we had? Like, again, everybody's intercept, like that beta naught gets multiplied by 1 forever. That's really what this is saying. Beta naught gets multiplied by 1. Okay, and then here's, right, we've got our beta 1 gets multiplied by time, right? So beta 1 gets multiplied by this value. Right? It again varies across time and it varies across people. So, and we could use that actually. We will use that. So that's my model matrix for model 1. We've never looked at this before because it's not that exciting. It's just like our time variable and our intercept. But I think you'll see that it's useful. Yeah.
Individual observations or people?
These are individual observations. Yeah. This is actually, yeah, if you look, like this is the first person. And then see how it starts again. So this is literally like, you will, this is the design matrix that is actually being used to like compute your, your model. And so there is, it is as many rows as you have in your data file. It's one row per row in the data file. And if you look at it, you'll see that it literally, this basically is the experience column from your data file. That's all it is. You went back to your data file, you can see this exactly maps on to things. But what's different about it is it's added to column 1s because the intercept always gets multiplied by 1. So we can see that. Okay. So it's not that interesting, but again, I think it becomes more interesting when we have some of these other models because you can sort of see, it allows you to see really easily. I mean, you can see in your data file too, but allows you to see really easily if you've sort of fit things the right way. Okay. Okay. Is the covariance between the time slope and the intercept statistically significant? Right. So, we have this question that comes up over and over and over again, right? Is it fair to interpret that covariance? So, see here, we can look at that. I fit another model, model 1B, fits the model with no covariance between the slope and the intercept. So let's go ahead and look at that quickly. All right, here we go. And you can see that the deviance for model 1B is 4935.4. So actually, yeah, do you see that? The change in the likelihood ratio test is basically almost 13.958, which means that the model that includes the covariance actually fits better than the model that doesn't include the covariance. So, I mean, that's kind of good news for us. We should keep the covariance, and B, it does then make sense to interpret the covariance, right? So, okay, so that we've done that before, but just sort of showing that again. Okay, here's something we haven't done before. Because, as a general rule, I favor likelihood ratio tests for determining whether variance components are sort of, necessary or not, right? So we've spent a lot of time comparing models with and without covariances using likelihood ratio tests. But you might want to have confidence intervals for those variance components. And another way that people sometimes look at whether variance components are, different from 0 is to actually look at confidence intervals for the variance components. Like the reason that I didn't bring it up until now is, again, I prefer likelihood ratio tests under, generally under most circumstances. remember we talked about all of these issues that are involved with, like, we can't assume that the variance components would be normally distributed, right? That the sampling distribution would be, or that they would be normal. So, even using these is like a little bit controversial in the sense that there will be people who will say like, people generally say you shouldn't test the statistical significance of the variance components. You'll get another group that'll be like, yeah, but I can live with the confidence intervals. And then you've got another group that's like, you shouldn't even use those. So I want to introduce them, but I also just want you to know that I think it's considered best practice to use the likelihood ratio test that we've been talking about. And if you're going to use confidence intervals, it is important to use either the profile method to compute those confidence intervals or the bootstrap method to compute the parametric bootstrap to compute those confidence intervals. And even still, again, they're not like perfect, but okay. I don't know that we're going to run the parametric bootstrap right now because it actually takes a while. So we'll run the likelihood one. And it's not horrible, but it takes a couple minutes. So I don't think we'll do that. But let's run the profile one. So if you want confidence intervals, all you're going to do is say const int. So this is, you have to first run your model, right? And then you're going to say const int, and this is the model that we just ran, weight 1. I put in here method equals profile, but technically you don't have to put that in because it is the default, but so I put, and also because here I've got method equals boost. And then there are other methods too, but you don't need to know about any of those because you should use one of these two. And then this is really, really, really important, something I discovered recently that will make your life easier, which is put in old names equals false. I know, that sounds really weird, right? So old names equals false. I did not know this trick until recently. So maybe I'll show you. I'll show you why it's so important by taking it out at first, and then you'll see why it's a nice thing. Okay, let's take out, but we're not going to do that with the bootstrap one. Okay, so we want these confidence intervals for a random effects. Actually, even the profile ones they're not like immediate. It's going to take a second. But the bootstrap ones take way longer. What do you notice about, so this is old names equals true, by the way. So what do you notice about old names equals true for these confidence intervals? The names suck, right? What's sig 01, sig 02, sig 03? Sigma you can guess is sigma squared, right? But which one is 01, 02, and 03? And then of course, like intercept is an intercept. And experience, that's the slope. So those are obvious, sigma squared, intercept, and slope, but it may not be obvious to you. Now, if you go back and look at your parameter estimates, you can figure it out because the parameter estimates should sit between the confidence intervals. But now watch if we put this in. All names equals false. Yeah, I'm just so tickled that it's the little things in R that make you happy.
I want you all to know that I did not learn this when I took HLM, and I was looking at those intervals and looking at and trying to figure out which one to fit in the middle and which, like,
Yeah. So look at this.
you should appreciate it.
Miraculous. It tells you what they are. I know. Seriously, I did not know this for a long time.
I didn't have that.
I
I'm not
didn't know this when I first started doing multi-level R. I used those stupid old names for a long time. And when I discovered this, I was like, okay, I'm going to make a big deal about it because it's actually quite nice. So you definitely want old names equals false. When you run let me say a couple things about the parametric. First thing I want to say, you will not get the exact same confidence interval, the profile likelihood and the bootstrap method. They're being computed using different techniques, right? One you're bootstrapping your confidence intervals, and the other one you're using. You will see, and I can't run them, but they're in your output. They're in your R markdown right now, but I'm not going to run the bootstrap. But you will see they're close. I mean, like they're really close, but they're not exact, But they're going to tend to in this case, they tend to be really, really close. If you're going to use the parametric bootstrap, which everybody know, okay, so does everybody know what bootstrapping is? Yes? Okay. In a nutshell.
There's a no in the back.
There's a no. I see a couple no's. So in a nutshell, like we use bootstraps when we don't have a good analytical solution for, I mean, often we use it for things like confidence intervals or standard errors. So like, which reminds me, standard error was something I wanted to make sure everybody understands. What's the standard error? Anybody? I know this comes up in every stats class, but I noticed that there was maybe not total confidence and whatever about what standard errors are. So, turn on the recording, by the way, didn't I?
Mic is on.
Recording's in progress. Okay, I was like, thank you. Okay, just making sure. Just making sure. Okay, what's this? That gave me time to think. What's a standard error? Anybody? Yeah, so
Standard deviation.
there was a lot of good stuff in there. I would cut out a few of those words, but generally there was a lot of good stuff in there. So
The gist is.
the gist is there. So think of the standard error as the standard deviation of the sampling distribution. And the sampling distribution is, remember, we've got this parameter estimate, but we don't know what the true parameter is, right? But you can sort of imagine, I mean, again, think about, imagine you repeated, like, again, we're always assuming, which we never have, that we've got like a random sample from the population. So start with that lie and let's go from there. So we got a random, random sample from the population, like never. But let's pretend we have a random sample, right? Your life is alive. That's right. Well, once I go through this, then you'll appreciate bootstrapping all the more. So imagine that you have like a random sample from a population, right? And so you just have this one random sample from the population. You get these parameter estimates. You get this set of parameter estimates, right? But they're just estimates. There's some population parameter. So imagine you were to draw again, right, and get another random sample from the population and estimate those parameters, right? Get a set of parameter estimates and so on and so forth, right? So like the standard error is really about it's the standard deviation of the sampling distribution. And the sampling distribution is sort of telling you about like what would you expect that distribution of estimates, right, to look like. Right? So there is some true parameter value out there. And what would sort of if you were to sort of, again, you don't do this, but if you were to repeatedly sample over and over and over, sort of infinite times, and you were to do this over and over and over again, what would the standard deviation of that distribution around the actual true parameter estimate look like? And one of the things that drives the standard error is, I mean, obviously the standard deviation of the outcome or whatever, but the other really big thing is the sample size, right? Because if I repeatedly sample 10 people, right, and I get some sort of an estimate, and I do that over and over and again for like lots of samples of 10 people, like the estimates are going to vary. I mean, theoretically, they should still like, in essence, the mean of those estimates should still give you the parameter itself, but the variability is going to be a lot higher because you only have 10 people, right? So one of the biggest things that actually drives standard errors is the sample size, right? So the larger the sample size, the smaller the standard error. Now that story gets a little bit more complicated, and we will come back to that in our last week when we talk about power analysis and multi-level modeling. The story's a little bit more complicated in multi-level analysis because, like, what's the right sample size, right? Is it the total number of units? Is it the number of clusters? Is it the effective sample size that we talked about on week 1? Whatever. Okay, so that's right. So that's the standard error. The standard error is the standard deviation of the sampling distribution. And the reason we compute these, and then what we usually do is we take like our parameter estimate for almost every statistic that you've done in all your classes, you take like the parameter estimate and you divide it by the standard error, right? And you get some sort of a ratio. So for a t-test, right, there's some critical value of t. You take the estimate, right? You take the parameter estimate, you divide it by the standard error. And if it's greater than whatever the critical value of t is, we say that that's statistically significant. Critical value of t is somewhere usually in the, right, somewhere close to 2 often. If it's a z-test, if we're using a z-test, then the critical value is 1.96, right? But we do the same thing. We take the value, we divide it by the standard error, and we sort of say, oh, okay, it's statistically significant. Why 1.96? Why is that the magic number? Yeah, because again, if you look at the bell curve of the standard error, right, then we're, or the bell curve of, the distribution, right? Then we're saying that like 5% of the time, or, less than 5% of the time or whatever, we would be outside that range, right? You'd be more than 1.96 standard errors away if from zero, whatever. So that's kind of the logic there. So we use standard errors all the time. We basically compute standard errors for every single statistic that we ever do in stats. But it turns out that sometimes it's not so, like, it's really easy to figure out what the formula is for the standard error of the mean, or the standard error for t-test, the mean difference. But sometimes in statistics, there isn't like an easy, so there isn't an easy closed form solution for the standard error. There's nothing that is quite right. And this is one of those cases, actually, and this is one of the reasons that like we have to be careful about confidence intervals and all that kind of stuff. Because remember we talked about boundary constraints for variances. Do you remember I said that, like, if we're testing this null hypothesis that the variance is 0, well, the variance can't be less than 0. So you wouldn't expect to get this nice normal distribution around a variance of 0, right? And so testing variances for statistical significance is incredibly hard and troubling and problematic. Okay, so the bootstrap is basically, we use a bootstrap when we don't have a good analytical solution for deriving usually a standard error. So there isn't a formula out there that can tell us how to get a standard error for something. So instead of like using some sort of an analytic solution, we just do it ourselves. And that saying of pull yourself up by your bootstraps, that's where bootstrapping comes from. So the idea is like, I can't compute a standard error. There is no like, there's no equation I can use. So what I'll do is I'll just come up with the sampling I'll come up with an estimate for the sampling distribution myself. So how am I going to do that? I'm going to just take, like, let's say I've got a sample size of 1,000. I get this parameter estimate, right? So I can bootstrap by basically taking a certain number of samples of size, usually it's the same size that you had, so size 1,000. So let's say, in this case, I say 2,000. So I take 2,000 samples of sample size, and this is not exactly what we're doing here, but just hold on for a minute. I take 2,000 samples of sample size 1,000 from my original sample, and I compute the parameter estimates for those 2,000 samples, and then I can look at the distribution of those parameter estimates, and that gives me an empirical estimate of my sampling distribution. Because I didn't have any formula or equation, I had no way of actually computing it analytically, so I just do it myself. That's what bootstrapping is. Now, this is not exactly what we're doing here, because we're using a parametric bootstrap. So a parametric bootstrap actually uses, let me say one other thing. You might be thinking to yourself, this is an important detail. You might be thinking to yourself, if I just take 2,000 samples of size 1,000 from my sample of 1,000, won't I get the same number every single time? How does this work? But the reason that it works is that we're sampling with replacement. So some people can end up in the sample many times, and other people might end up in a given sample no times. And it turns out that this actually works really, really well. Now, we're not exactly doing that here. We're using what's called a parametric bootstrap. So we're basically we're using our, we're not literally like bootstrapping the whole sort of thing. We're using our parameter estimates, and then we're sort of using these bootstrapping techniques to kind of deal with for the error piece. And you really, you really don't want to use a non-parametric bootstrap when you're doing multi-level modeling, because a non-parametric bootstrap doesn't take into account the non-independence in the data. So like if I literally just did a regular bootstrap and I have this clustered data, that wouldn't be good, because it wouldn't actually, did you follow what I'm saying? You'd just be like treating each person as if they're independent. Remember what I just said about like some people might show up not at all and other people might show up in observations or whatever many times. So a parametric bootstrap is just basically like another way to get these confidence intervals where we're not literally just kind of bootstrapping the entire data set, but we're using bootstrap techniques to kind of get better estimates for our standard errors. Okay, enough said about that. So if you're going to use bootstraps, you probably want to say something like parallel equals multi-core, because that, if you have multiple cores on your computer, because it'll make it run faster. And then this is the number of CPUs, 8. So I put those, if you don't have 8 CPUs in your computer, I guess you should change that to a lower number, but that'll make it run faster. But even, even the parametric bootstrap takes a while. So we're not going to run that, but those are your confidence intervals. All right, so you can also, as I said, you can use the package parameters to come up with confidence intervals as well. So that's all I wanted to say about confidence intervals. So now, what time is it? I'm afraid to ask. Okay, well, we'll get through this example, but we're not going to get through the next. I'm glad I changed the homework. Okay, so model 2, change in level. Are you ready? So again, all the magic has kind of occurred in the coding outside of this. So it looks just like model 1, really, except that I put in GED as, another predictor. Now in model 2 here, you can see I'm not allowing the GED slope to vary across people. I think I've got a model 2B coming up in a second where we can compare those two models. But so let's just run this model first. It should run really fast. And now let's look at our model matrix for model 2. Okay. And it only ever shows the first 1,000, by the way. Okay, so again, so you see it looks very much like our old model matrix, except for now we can actually see, right? We can intercept, right? Time variable. Now this is the GED variable, which is either 0. Okay. All right, so model 2. Here's our output. Maybe, I hope. It's taking a while. Oh, because of the confidence intervals, that's why. There we go. Da, da, da. Okay, here we go. So, okay, so let's take a look at our model 2. So you can see that the intercept is 1.7, not 2. Period 0.045. I think that was pretty similar to what we had before.
Yeah, we did write all those down.
That's okay, but it's pretty similar. The GED slope is 0.068, which means that, so this is saying like every year that your wages go up by 0.045 a year, right? For every year you work. But then when you receive the GED, boom, there's a change in, remember it's a level model, so there's a change in level. Basically, you get a jump of 0.068 in terms of your wages. And again, natural long wages, I know that doesn't mean much to anybody, but like, that's more than a 1-year increase in wages, less than a 2-year increase. About whatever this jump is, it's about equivalent to a 1.5 years of pay raises, right? So I can kind of make sense of it in that way. And you can see that here I used for the, I kind of skipped that part where I talked about it above, but you can see I put in like confidence intervals, and the confidence interval method equals profile. And so you can see here now, this is another way that I can get the confidence interval for my random effects, right? And This is even better. I didn't even have to map them back on because. Yes.
Do we know that it's causing the jump, not affecting the slope?
No, because we don't know that yet.
Right, but is that because we didn't put it in? I know it's labeled that, so I change in level, but looking at the
Oh,
code,
the code is because I didn't put it into, not the parentheses part, but go back up here. Right? I've got experience.
Yeah.
This is my time slope.
Yeah.
And this is GED. So I don't have post experience, which was the post time slope. What I was saying about this is you can see I didn't put in GED as randomly. But here you can see I only have just the change in level because this is like this is experience is our regular time change in level. That's all we've got so far. So right now we know, so just going back to our logic, right now we know that a change in level, we do get a statistically significant change in level, but we haven't put in the change in slope yet. So maybe that doesn't matter, right? The next, oh yeah, the deviance is, the
Love
deviance,
your bandana.
oh yeah, you know what? I don't think it doesn't show the deviance in, does anybody know? Thank you. 4906. I was going to say that's one thing that kind of stinks about the way I just had this printed out. Okay. With what?
Doesn't give her a point anything.
Okay, that's fine. Okay, so right, so I could compare models 1 and 2. Oh yeah, here's where I did it. There you go, 4906. So if I compare models 1 and 2 with ANOVA and with compare, you can see that actually, right, model 2 definitely fits better than model 1. There's only 1 degree of freedom difference here because I added a fixed effect, but I didn't allow for a random effect for the GED slope. So far model 2 is in the lead. But what about this random GED slope? Should I allow it to randomly vary? Okay, well, here we go. Model 2B is going to allow, see here, model 2B, you can see I'm allowing GED to randomly vary across people, right? So how many, compared to model 2, how many parameters am I adding? Got to think through that tau matrix, right? Because it's a variance for the GED change in level. And then it's also a covariance between that and the time slope and a covariance between that and the intercept, right? So actually, by adding just this one random effect, I'm adding, I think I counted right, 3 parameters, right? So let's go.
I counted 3 too.
I was going to say, you have to think about the tau matrix in your head. Okay, so we ran that. So now let's take a look. Ta-da! Oh, by the way, so you can see this is kind of concerning, right? We do get results here. And I think I was planning to talk about this a bit more next example, but kind of mention it here too. Do you see that it says like the model failed to converge, right? So, convergence code, so like optimizer, convergence code 0 is okay, but then it sort of failed to converge here. So like, these are the kinds of error messages that you're going to start to get pretty frequently when you try to estimate random effects and they're very close to zero. So, that would be, in my mind, likely to be indicative of part of the, like, my first thing when I see something like this is, oh crap, I'm trying to estimate like too many random effects. And at least one of them is probably like near zero. And again, especially in longitudinal models, because we don't have that many time points, it becomes problematic. Okay, so let's go ahead and look at the let's look at the ANOVA and the ANOVA. Okay, so I mean the bad news is that actually, let's see, right? Model 2B does actually, well, no, actually, I don't know. It's a toss up, right? If you look at this. Model 2 and 2B. The chi-square is like, oh, God, I hate this. So here we go. Look at this. The chi-square statistic. AIC is actually, so it's, no, the AIC is lower for 2B, right? The BIC is lower for 2. You see that? This is one of those like bad situations that you will often find yourself in, where you're sort of getting a bit of like mixed evidence about whether you should sort of retain or not retain that slope. Now I'm kind of forgetting what I decided to do. That's bad, right? My God, I really belabored this. So then I fit a model where I did not allow the GED slope randomly varies, but I'm not allowing the GED slope. I'm not allowing the GED slope to covariate. I could fix the covariance. And that's model 2. Look at model 2C. See? Oh, and it's actually, if you look on your, I guess I can show it in visual. So what does tau matrix look like?
So it's just GED, you didn't allow to covary with anything?
Yeah, GED is,
But the others,
yeah, exactly. Oh, shoot. Put me back up to the top. Hold on. Where was it? Not model 4, model 2. Model 2.
Describing them.
What? Here's it. I have the pretty matrix.
I can give it to you.
Oh, yeah, thanks. Oh, wait, yeah, okay, I'm not there yet. Descriptives, blah, blah, blah. Here we go. Change in level. Ah, there it is. I just saw it. Okay, so here we go. So what does this tau matrix look like? So here I'm saying, right, if you look at this, I'm saying like, okay, like the slope and the intercept, they're allowed to they're allowed to covary with each other. But when I put this 0 plus GED here, I'm really saying like GED is not allowed to, right? Like it's not going to covary with the intercept. It's not going to covary with experience. I've got this sort of second, I've got this like second set of parentheses. And so this is actually the structure of the tau matrix in that case. So I'm really saying like, okay, this, if you think about it, right, this is just like our regular linear growth slope tau matrix. I'm allowing the slope and the intercept to randomly vary and covary with each other. And then I'm saying, okay, well, maybe I could estimate a GED. Maybe I could estimate the GED slope and allow it to randomly vary, but I just won't allow it to covary with the other things, right? Does that make sense? Yes.
Clarification. So tau 10 and tau 01 are functionally different.
They are equivalent,
So in the letter, it's tau 10 and tau 01.
but they are the same thing. But it's the indexing. Yeah, this is the row and the column. So tau naught 1 is the same as tau 1 naught. So it's right tau, like we get this as row 0, 1, 2, and this is column 0, 1, 2. So they are absolutely, there are only 3 unique elements here, right? But yeah, they're
It
not.
doesn't matter which one you label it.
Well, I mean, it doesn't really matter which one you label it if I ask you about it, but like in the matrix, it really should be this way. Did I say it wrong? Maybe I did it wrong. It should be row and then column if I did it wrong. What?
Well, I think it's big.
It should be. So row 0, 0, right?
No, this one is, this one.
Oh, yeah, I'm totally capable of messing it up. But
It's
it's
probably
probably,
you had it as 01 and.
yeah. No, I could
So,
totally,
like,
I could totally mess it up. But technically, and they are the same. So in some sense it doesn't. But technically, when you do these, you should always put the index for the row first column. And then, again, like in it, but like if you were really you're telling it like pull from this row in this column, that is anything in matrix algebra comes first. Anyway,
Take multivariate response.
right? Yeah, it matters. Like it doesn't matter for anything we're doing because they are the same, and we're not actually manipulating matrices, but it does. That is the way you should do it. So I apologize if I messed it up. Yeah, but the double bar won't give you exactly the same thing because the double bar will have them all be unrelated to each other. So if you did the double bar, yes. Well, by pulling out two, yeah, so you could use the double bar with two separate. Yeah. Totally, you could totally. Yeah. But if you just try to do like all of it with the double bar, you could get, I think what you would get is just the variances. Yeah. Okay. All right. All right. So let's see. Oh yeah. So let's see. How does this fit? Oh, have to force to actually run the stuff. At least it didn't put me somewhere else. Okay. So how does this fit? Again, so 2B and 2C are actually about the same. And 2 and 2C, no, 2 and 2C, so 2 still fits better than 2C, right? Although, again, sort of mark. So, okay.
So overall, we're going with 2.
Or 2, let's see, there were 2 loser models. 2B. 2B fits better. Is what I meant to say. 2B, the most parameterized model actually in this case fits better. Sort of sadly in some ways because it's probably too parameterized. All right. So and you're going to see that when we get to model 4, I think we're going to have even bigger problems making everything randomly vary. But okay, model 3. Let's get to model. I want to make sure we get to models 3 and 4. So model 3, changes in slope. So here I'm taking out GED and I'm putting in post-experience. Again, at first, I'm just going to do it because I'm like not feeling great about my random effect model. So like at first, let's just run it with with experience, but not with post-experience slope. Right? And now let's look at our model. Well, you don't have to look at the model matrix there. I think you got the idea of that. There we go. Okay, so here, this is interesting. So now again, we're still not to model 4, but our intercept looks very similar, 1.71. Our experience slope is 0.042, so we're growing about 0.042 points per year. But our post-experience slope is 0.014. And remember what that's saying, right? This is not like a jump. This is really saying before you get your GED, you grow at a rate of 0.042 points per year. But and I haven't allowed for discontinuity, like right at the point at which you get your GED, but after you get your GED, you grow at a rate of 0.056 points per year. Why do I say 0.056? Because it's 0.042 plus 0.014, right? So the post-GED growth rate is this plus this, because I use the change in slope kind of coding, right? And that's statistically significant. Oh, and what's the deviance? Yeah, the deviance. What was it? Okay, thank you. And again, I can look at model 3B, allows the post-experience slope to randomly vary. And what's kind of interesting here is, unlike model 2, so let's just put the random effects thing a little bit on the back burner for model 2. We'll come back to that if it's our best model. But what's interesting here is, wait for it to run. Stupid confidence intervals. Now you see why I don't always put them in. I should have taken them out at some of these. One's taking especially long. Annoying. But anyway, what you're going to see when it comes up, when the confidence intervals are done, is you're going to actually see that for model 3B, unlike model 2B, which did fit better than model 2, model 3B allows for the post-experience slope, doesn't actually fit significantly better than model 3. So in the case of the post-experience slope, you really don't need that random. Let's see. And actually, so I wrote it here. The chi-square change is 2.61 degrees of freedom. So, and like, I don't have to necessarily go in and remember in model 2C, I was like digging in to see, is it the covariances or is it the variances, right? Like, do I need, but like, in some sense, it doesn't really matter because with a chi-square change of 2.61 with 3 degrees of freedom, I can get rid of all 3 of those parameters and my chi-square only went up by 2.61. So like, you know, I can look at, there's a model 3C and I could look at that, but like, that's not probably going to be, not going to be my best model, right? Okay, so comparing the original model 3 to model 2, let's just take a look at those for a second. So we've got 4912, right, to the original model 2, which was 4906. So again, these models aren't nested, but they do have the same number of parameters, right? So I can literally just compare the deviances outright because the one that has the lower deviance will have all of the ICs will be lower, the AIC, the BIC, everything. So this suggests actually that model 2 fits better than model 3. See that?
So far, we're at model.
So model 2 fits better than model 3, but again, everything was statistically significant across the 2 models, and really, we still need to see model 4. Model 4 is like where all the action is in some ways, because it's going to kind of tell us what's going on. Let's see. Oh, maybe I should run these, because people were asking about predicted values. So let's see here. Run these. Okay. So just quickly, if you want to use the effects package to come up with predicted values, if you're doing it by hand, it takes a little getting used to, but here's, I can create, so I'm always kind of creating it as an object. So I say effect, and I'm using capital E. There's actually a difference between the capital E effect, and then here I'm saying, okay, so here I'm saying for experience, I'm using the model wage 3. This is like one of my independent variables, but here X levels is like, okay, so for this covariate, what levels do I want to actually get the predicted values for? And I'm saying, and I looked at the data, by the way, to like what's the range of data. So I wanted to go at 0 because that's like where the intercept is. And I think the range was like from 0 to 12 years of work or something. Because remember, this is years of experience. So I said, oh, I'll go like 0, 2, 4, 6, 8, 10. That's easy, right? And then the way that I did this here is I just said, okay, given, because again, like, think about it, because I've got like a slope and a change in slope, I sort of did, okay, given values where post-experience is 0. So this first one is going to give me, if you didn't have your GED ever, I'm going to get those predicted values. And then here I did the same thing, actually. And now I did 2, 4, 6, 8, 10, right? Like given values of post-experience of 2. Why do you think I did it that way, by the way? And then I did the same thing here. 4, 6, 8, 10 with post-experience of 4, 6, 8, 10 with post-experience of 6, 8, 10 with post-experience of 8. Well, yeah, like, why wouldn't I have just gone 0, 2, 4, 6, 8, 10 with post-experience of 2? Like, there's no, yeah, remember, like, the very lowest that post-experience could ever be would be the same as experience, right? If somebody already had their GED, then their post-experience and their experience are going to be like the same, you know? So it doesn't, anyway, it made sense to me. So it just gives you, and then you can sort of see like, okay, right? This is somebody who has like no post-experience. Those are their predicted values, right? And then you can jump from this one and say like, you know, right? So what's their predicted value if they've got like, you know, 2 years of experience and their post-experience is this and so on and so forth. Okay, I digress. I'll move on from there. Let's get to the real meat of the matter. So wages, yay. We're going to put in everything here. We've got the intercept. We've got the post-experience slope, the GED slope, the experience slope. It's all there. And again, just for simplicity right now, I'm not allowing for anything to randomly vary other than the time slope and the intercept. If you look at my model matrix, oops, let me pull that up. Again, if you look at my model matrix, you can see, oops, where to go? You can see, it keeps going. You can see again, the intercept, the experience slope, the GED. See, this is exactly what my data file looked like, almost, right? Except for the intercept. Got the experience, got intercept, experience slope, GED slope, post-experience slope. That's everything that's going into my model. Great. Now, scrolling down, summary. Okay. Oops. There we go. So here we go. This is where the rubber meets the road. Let's take a look here. We've got intercept is 1.7. It's 0.043. Okay. And that is statistically significant. GD 0.056. That is statistically significant. And again, this is the effective GED once you allow for that post slope to be in there, right? This is the effective, this is the post slope once you allow for discontinuity in GED. And what do you see? It's 0.0068, and it's not statistically significantly. Do we see that? So once I allow for that change in intercept, I don't actually need a change in slope. So if I didn't allow for a change in intercept, I needed a change in slope. And if I didn't allow for a change in slope, I needed a change in intercept. But when I put them both in together and let them battle it out, it turns out once I allow for a change in intercept, I don't actually need a change in slope. Does everybody see that? Okay, great. So let's look at the deviance for this model. It is, where is it? On deviance. Okay, here we go. Deviance for this model is 4904. 0.3. Oh, you're ahead of me. 4904.
I looked ahead because I wanted to down.
40, okay, fair enough. 4904.3. And again, let's compare this to model 2. Let's forget about the whole like random effect stuff for a second. So this is totally comparable to model 2. And the difference is how many parameters? From 4 to 2. What did I add? Because in both cases, I have a randomly varying intercept and a randomly varying experience slope, and that's it. So the variance components are basically the same across these two models, which is one of the reasons I kind of like doing it this way anyway. So the variance components are the same across these two models. So what is different? I put in both the post-experience slope and the GED slope. So the only difference is that there's a post-experience slope in here too. So I have one additional fixed effect. Right? So the change in the number of parameters is just 1. So I would compare the difference between 4906 and 4904, right, to a chi-square with 1 degree of freedom. And it's a 2-point difference, but I would need a change of at least 3.84 for this model to be statistically significantly better than model 2. right? So model 2 is my best model. Okay, and the bad news there is then I gotta go back and, I mean, like, if this were your model, then you gotta kind of think about what are you gonna do with the variance components? Model 2. You know, go simpler or more complex. But model 2 is definitely the best fitting model. So what does that tell us? It tells us that once, you know, that really, it looks like GED has more GED effects. It has this model would suggest there's an immediate effect on your wages, but it doesn't actually change the growth in your wages, right? So people get a GED, they get some sort of an immediate bump, but then like the growth slope for their wages is basically the same both pre and post. And you can see that even from the parameter estimate, which that post-exposure slope, which was not significant, is literally like 0.0068, right? So very small, although all these numbers are kind of small. I mean, that's the other thing about it. You don't know what small and big are until you know what the metric of everything is. But okay, questions about any of that? Yes. It's a slope that gives us the change in level, right? Like every level 1 variable you can think of as a level 1 slope. It's the GED slope, but you're right that the GED slope is coded as a 0, 1 variable, but like gender, we called it a gender slope, right? And that was a 0, 1 variable. So I agree. It's like, in a way, it seems confusing, but it's a level 1 slope, but what it's capturing is actually a change in level. Yeah? Other questions? Does all of this make sense? We might end early. Did we cover everything? Well, I'm not going to start the next packet now.
No,
That would be foolhardy.
And the other stuff that you talked about earlier is in the next packet. Done some of the.
Oh, that's good. I have already done some of this. Okay, so let me just talk for a minute about what you have to do for your homework. How about that? So for your homework this time, you're going to fit, and that is true. So there's a bit of repetition actually in the example that we do next week as compared to this week. So I'll go through the first part of next week's example more quickly because we're going to talk about a piecewise model, but which is basically the same thing as these discontinuous models that we're talking about. So your homework is a piecewise model. It's exactly what we talked about, like coming up with those different pieces for like the different slopes, right? Like 0, 0, 1, 2, 3, those kinds of things. So your homework is basically you have a model and it's the model is 4 time points and you're asked to compare a linear growth slope to a piecewise slope where you've got slope 1, I think, is time points 1, 2, and 3, and slope 2, or 1 through 3, and then the second slope is just goes from time 3 to time 4. Very little slope. So you need to do that, but what you do need to do is you do need to create the codes. So you have to create the codes for the different slopes, for the different pieces, for time and for the growth slopes. And in fact, I ask you to make those codes and to put them into a table in your homework, and then create them in R. So like, I don't want you to just create, just like we did here. I want you to kind of, map them out here and then get them into R. And, again, if you're having trouble figuring out how to get that coding into R, you've got it all mapped out, come and see the TAs or see me. We're glad to help you. There is some code did we give out the next packet?
We did not. We can.
Let's give out the next packet because the one thing that I didn't show you today, but is right in the next packet, is there's some really simple code that you can use to create those time variables. I mean, you could do it lots of different ways. You have the capability of doing it already, given the things that you know, but there is some simple code in here too, if you want to use it. So you'll see that. So you're going to fit a linear model and a piecewise model. You're going to compare them. There are a few questions that you're going to answer about those, and then that's it. And I think it's relatively straightforward. And then next week's homework. So next week we will do a quick review of piecewise models, which So that is in this packet. And then we're gonna extend it, actually, what the big difference is, we're gonna extend it to a three-piece piecewise model, because the example that we're gonna do is a three-piece piecewise model, which we're gonna compare to a cubic model. So next week, we'll do a quick review of piecewise, adding a third piece, and then we'll talk about polynomial models, and we'll go through quadratic and cubic models. Then we'll do an example that compares a cubic model to a three-piece model. And then at the end of all of that, oh, so then your homework next week will actually be to sort of compare the model that ran this week to a polynomial model for next week.
So I just want to also say one thing, that first one where she asks you to make the table of the coding, it says describe them in a table, and you don't want them to like write out stuff. You just want them to like label.
Oh,
the
yeah, I'm
table.
sorry if I said describe. I mean, describe, what I'm really looking for you to do is just give the coding scheme the way that we did on the board, like how I made like, oh, this would be 0, 1, 2, 3, 4, this would be 0, 0, whatever. That's what I'm looking for. You don't have to like wax poetic. Oh, you don't have to wax poetic verbally and describe the table that you've made. I just want it to be outside of the R code, that I can see that you're, thinking through the coding correctly. And if you're having trouble, that will also be easier for us to see if you're having trouble with thinking through the code, like thinking through how to create the variables, or if it really is just like an execution. All right, that's it. See you next week.
Just anticipated questions on that.
Yeah, no, that's good. And you have to, I said this in the bottom, but I tell you, you need to grand mean center the level 2 variable. It says, grand mean centered I put a little note on the bottom. That means you have to do it. So, right, do it. Grand mean centered. Don't assume it's grand mean centered. Check if it's grand mean centered and grand mean center if it needs to be. So you're basically creating all your own variables this week. Isn't that exciting? It was exciting.